Good morning. Oops. Good morning, everybody. Just get my drawing program ready. And then we will be good to go to continue our discussion on fractions. We have a little more to do, just a little bit, as soon as I have something to write on. All right. Okay. So let's give this title Fractions and Decimals. There is a more efficient way to represent fractions and look at fractions as we move from the leftmost basic intuitive side of understanding. As we move to the right, there are properties and ways to do things that are more efficient, more effective. Using decimal numbers as representations for fractions and mixed numbers is one of those things. So if I just do this by example, well, not first, let me just set this up. So if we just look at integers, we have our hundreds place, hundreds and tens and ones, and then we can go smaller, still based on 10, and have tenths. And then we separate that by our decimal point. And hundredths, and so on, in either direction. Now it's still based on powers of 10. They can just get smaller and smaller as well, past the whole number parts on the left and the right of the decimal point. So let's see what we get with some exercises. One way to, well, the main way for us to convert a fraction to its corresponding decimal representation is by using long division again. So we have these three. So let's have a look. So that's exercise 1412, number 1. We have 5/20 is what? So we want to look, we're not changing the quantity that it represents, we're changing the representation. So this we saw with our division last time, that the top, well, this is really sort of equivalent to 5 divided by 20. That in certain basic division instructions where I can't even fit the group size in, I just get my fraction that corresponds exactly to the division, saying that these are actually equivalent when I interpret them. So that means that the 5 is going to go inside my house, the 20 is going to go outside my house. Now we haven't done long division that much with multi-digit numbers as the divisors, but 20 is not a bad one. So we won't go crazy with these. So we start by saying 20 goes into 5 0 times. Then I still have something left. I now need to keep going until I don't have a remainder anymore. So I'm going to have my decimal place, and then just shift my view, just like we shifted our view from thousands, hundreds, tens, ones, and so on. I'm just going to keep shifting it to the right. And when I do that, the method doesn't change. it says, look at this relative to that position, which then makes it 50, because this is 50 tenths. 20 goes into 50 two times, and I have to keep everything in line there, because it's really 20 goes into 50 tenths, 2/10 of a time, I suppose. So 2 times 20 relative to the position is 40. Now it might bother people to see the decimal point there. If it bothers little Timmy, leave it out for a little bit. We know it's there. As long as it's there in the answer, separating those positions, it's okay. So do whatever makes Timmy comfortable. Because this division method allows me to sort of look locally and forget where I am in the larger scheme of things. So it's very convenient for that reason. 20, so then I take that away. So I have 10 left. 20 doesn't go into 10. I need to, because there are many zeros here, right? I'll keep the decimal place. I have another zero I can bring down whenever I need to. 20 goes into 100 relative to this position 5 times. 5 times 20 is my 100. Take it away. I have nothing left. No remainder. So the decimal version of 5/20ths is 0.25, 0.25. Now, yes, there are other ways to do this. You could look at an equivalent fraction and put it over a power of 10, but that's not always going to be so easy to do. In this case, we start with a nice simple example. Long division will always get me there. And then the benefit of having a decimal number instead of a fraction is when I do the arithmetic, it works in the same way with our methods that we've established before when we look at our number system. So it is much more convenient. But you lose some number sense when you start with this. You don't want to start with decimal numbers. Once you're comfortable with fractions, then we move on and see alternative representations and how it fits into the grand scheme of things. Let's try a couple more. 6 over 25. That means 6 goes in the house, 25 outside the house. I pick nice and easy denominators, see? Let me just check if there's any YouTube comments. I don't have it open. People don't comment often, but I have to be ready. All right, 6. 25 doesn't go into 6. 0. Keep my decimal point for positioning purposes. Then I need another 0, which is right there. 25 goes into 60 2 times. 2 times 25 is 50. I, of course, know relative to where I am, it's 50. I say 50, but it's not really 50. It's 50 tenths. Then I have 1 left. Well, really 10 relative to this. I need more zeros. Bring them down. I can look at 100. 25 goes into 100 4 times. 4 times 25 is 100. Relative to that position, I have nothing left. So 6 over 25 is 0.24. Again, you might say, oh, that was easy. Because we pick nice denominators to work with, it isn't terribly difficult, but we don't need it to be terribly difficult to demonstrate the method. Now I lost my last question. Where are you, last question? Let's do a 2b. Just take a super easy one. Because for little Timmy, he might have never seen 1/3, right? He saw it in his intuitive number sense building examples, drawing a rectangle, representing a third, visualizing it, that's all good. But when it comes to decimal version, maybe he's never seen it before. So let's do it. So we put 1 in the house, 3 is the divisor, 3 goes into 1, no, never. 0 times. So I need another 0. Now I can look at 10. 3 goes into 10 3 times. 3 times 3 is 9, of course, relative to where I am. So I have 1 left. Bring down another 0 because my remainder isn't 0 yet. 3 goes into 10 3 times. 3 times 3 is 9. And then you're waiting for little Timmy to say, but wait, this is going to happen every single time. I'm never going to get out of this loop. Every time there's 1 left. Every time it's 3 times. I'll go on forever. Yes, you will. So you see here, there's a repeating section, which means I'm never going to get a remainder of 0. This is going to go on forever. So there are decimal numbers that repeat forever. And we just put a little line over it. Some use a dot. I prefer a line to indicate that the 3 is repeating forever. Forever. So that's the downside, unfortunately, of decimal numbers. They're not as clean as the fractions are. Some of them have decimals that continue forever. It literally never stops. And we will talk about rounding a little bit later. You have to round this number to sometimes work with it, and that could lose some accuracy. So that is the unfortunate downside to decimal numbers. There's a trade-off. I think they're still worth it, even though I have this property. So some fractions are what we call a terminating decimal number. Some are what we call a repeating decimal number. They're both fractions, but really it depends on what the numerator and denominator are. Could result in a terminating decimal, could result in a repeating decimal. But luckily we only get those two. Let's just do one more. This is number 3. 13 over 12. Now let's suppose we want to leave it like this. Instead of converting it to a mixed number first, maybe you don't even want to bother with that. It really doesn't matter what form the original fraction is in. I'm still going to have to divide by 12. 12 goes into 13 once. 1 times 12 is 12. Take it away, I have 1 left. I need some zeros here. So I have, relative to that position, 10. 12 goes into 10 0 times. I haven't done anything yet. Bring down another 0. Now I can look at it as 100. 12 goes into 100 8 times. 8 times 12 is 96. So then I have 4 left. It's not quite enough. Bring down another 0 for 40. 12 goes into 40. How many times? 3 times for 36. 36. And then I have 4 left. Still not 0. Bring down another 0. 40 again. 12 goes into 40 3 times. And then I start to see, ooh, wait a minute. There's my repetition. Every time I get the same remainder, I'm going to get stuck in a loop. Now you can verify a couple of times to be sure. Don't wait for just the first one. Be sure you get it repeatedly. Then you see, it's going to keep going like this forever. So what I actually have here is a repeating decimal number. Even though I might have a couple of 3's in my answer before I'm convinced that it is repeating, only put a line over the first one that is going to be repeated. Alrighty. Now, I don't know how familiar you are with these things. Could be very familiar, could be not at all. I'm going to do a number 4. let's say 2 over 7. 2 is in the house, 7 is outside the house. Single digit, can't be that hard. 7 goes into 2 0 times. I need more zeros here. 7 goes into 20 2 times for 14. And then I have 6 left. 7 doesn't go into 6, bring down another 0. 7 goes into 60 8 times. 8 times 7 is 56. Oh, of course, all relative to that position. Then I have a 4 left, which hasn't occurred yet. 7 goes into 40, goes into 4, 0 times, bring down a 0 to make it 40. 7 goes into 40, 5 times, for 35. Then I have 5 left, that hasn't happened yet. Bring down another 0. These arrows help me keep everything in line. It's very useful. 7 goes into 50, 7 times. That doesn't sound right. Do I do this right? Sure. I'm just thinking of something else. For 49, that leaves a 1. Bring down another 0 over there. 7 goes into 10 once. 1 times 7 is 7. For 3, 3 hasn't happened yet either. Bring down another 0. 7 goes into 30 4 times for 28. I'm running out of space here. 28 has left 2. It's not 0 yet. Bring down another 0 for 20. 7 goes into 20 2 times. 14. Take it away. 6 left. Ooh, and now I see this has happened over here. It has happened before. So finally, I'm repeating myself. And the next one's going to be an 8, 5, 7, 1, 4, and so on. So it does repeat, and a lot of it repeats, a large section. All of this repeats over and over and over and over forever. So a repeating decimal doesn't have to have just one digit repeating. It can have 2, 3, 4, many. This one has 6 of them repeating over and over and over and over and over. Still a repeating decimal. So it's really, in some cases, I have to be patient and wait, see. If it comes from a fraction, it's going to either terminate or repeat. And it's just a matter of how big is that repeating section. Could be longer than just a couple of digits. And I have to just be patient to wait for it. Assuming, of course, I've done all my little divisions correctly. To make sure that at every step I've done it right, so that a single digit here isn't unfortunately wrong, then my pattern will get all messed up. So I have to be sure of all my multiplication tables, which is really what I'm using here. Okay, so that is one side of the coin. Which is from a fraction converted to its corresponding decimal representation. The other side is also there. If I'm given a decimal number, what is the fraction or mixed number that it comes from? Now, in some cases, that question is quite straightforward. Let's look at exercise 1413, and I'll just copy it down for us here. Number 1 is 0.378. In the case of a terminating decimal, this other direction, we've done the first one, right? This other direction is really not difficult, to the point where you almost don't have to say anything. If you understand what these decimal places mean, then the answer is quite straightforward. Let's suppose this way. 0.3 would be 3/10, because that's exactly what that decimal place means. 0.37 would mean 37 hundredths. So 0.378, as our example, is 378 over 1,000, because it stops in the thousands position. This is just a side note. So it's really as simple as just putting it over the appropriate power of 10. Let's look at number 2. It doesn't matter how late that is. That 8 is in the hundredths position. It's 8 hundredths. 5.95 is our next one. I don't care about the 5. I care about the decimal portion. I think almost it's better to do it this way, especially for what's coming up. This is just a 5, and 0.95 is 95 over 100. And I can then put it back into a mixed number, which is perhaps a more intuitive version. Or, of course, you could have gone 595 over 100 and have it as an improper fraction, whatever makes you happy. So in the case where my fraction is, or my decimal rather, is a terminating decimal, there shouldn't be any problem. However, when it's a repeating decimal, we have an opportunity to see something interesting that leads us into the next topic very nicely. I'm just going to pick a simple one, like let's just pick this 0.95, just randomly. 0.95 equals what? Let's suppose, just for a moment, I didn't know what to do here. I can do this in a much, much fancier way. Admittedly, I don't need it here, but for what's coming up, I kind of do. Where's another way that I can structure this and have it look much more mathy? I could say, let's give this a name. Let's give the decimal representation a name. Well, I have a question mark here. Let's just make it a more interesting question mark. Let's say question mark in a box. That is my symbol that I'm going to use to represent this decimal. It's going to be the fraction version that's hiding there. It's hiding behind that. Imagine I can peel this back like a sticker and it would show the fraction. But the sticker is there. I can't see the fraction. My goal is to figure out what is that fraction, pretending this is much more complicated than this specific one is. Okay. Well, what we can say then is, look, this is messing me up. The fact that this is a decimal number, it's messing me up. So let's just realize that, okay, this question mark in a box equals, it has the same value as 0.95. It's the same thing. Equal means it's the same thing. And I chose this symbol to mean exactly the same thing. So I haven't really said much. I've just sort of rephrased this this represent word into my mathematical word, which is the equal sign. That's all I've really done. Now I want to think of equations and what they really mean. They really are representing things that are in balance. So in the old days, you had these balance scales that people used to balance and see what's more than something else. If you put stuff on either side and it tips to that side is heavier. That side has more stuff, assuming all things are equal. If the scale remains in balance, then the two sides are equal. So right now I have an equal, so the question mark in a box and the 0.95 are perfectly in balance. If I now put two of them, I put another question mark in a box on the left side. I'm going to have to put another 0.95 on the right, and then everything will be in balance again. So if I duplicate it in the same way, everything's going to stay in balance because the original pieces were the same. So if I do 10 of these on the left, as long as I do 10 of these on the right, everything's going to be in balance. But now I want to pick an amount that gets me to not look at this decimal point. So what I'm going to do is I'm going to multiply each one by 100. I'm going to have 100 copies of the question mark. Then I better have 100 copies of 0.95 as well. Then everything will still be equal. So as long as I do it on the same side, sorry, as long as I do the same thing on either side, everything's in balance. So now I don't know what 100 question marks will be so far. So I'm just going to write 100 question marks is what I have on the left. Don't know what that is yet, right? But it is equivalent to, now what happens if I multiply a decimal number by a power of 10? Every time I multiply by 10, I move the decimal to the right. So because 100 has two zeros, 10 times 10, it's multiplying by 10 and then multiplying by another 10. So really, this is equivalent to 95. I can take smaller decimal examples to convince you that multiplying by 10 is just shifting the decimal point around. So the reason I took 100 was that I didn't want to look at this uncomfortable for me decimal point. Now there's no decimal point in there. And I just have my more familiar integers. Oh, it's 100. Oh, it's 95. Great. Okay. So now, and again, I'm assuming either you're not super comfortable with this, which is totally fine, or I'm thinking of this as from a teaching perspective. For someone that's never seen these things, never thought about balancing, never thought about equations, never thought about anything, I need to say it in a simple way that every little step I make doesn't feel like a big jump. So they can say, okay, I'll just put an equal sign there. It's still the same thing. Okay, I can picture the balance scale. Okay, I'm multiplying it by 100. That's why they're still in balance. It's the same. Okay, the decimal point shifts. So every little step I make is no single one is overwhelming. Yet we're stringing them all together to get to where we want to go. We want to make sure that no single line is a jump that is too big for your audience. And I'm thinking of my audience being little Timmy seeing this for the first time. I know where he needs to go. He's going to soon have to handle repeating decimals. This is going to help him. Right now, I'm taking a fraction that I know what the answer is and seeing how I can do it in a fancier way. And that fancier way becomes necessary soon. Right. So now, again, it depends on your audience. I'm going to go as basic as I can here. I have a multiplication sentence. Mathematical multiplication sentence. And he would have done that without the symbol. He would have done multiplication sentences. He would have done, for example, 2 times 3 equals 6. Look at the workbooks. They take this and they write it in all 4 of its versions. The other version is 3 times 2 equals 6. The other version is the 2 corresponding division sentences. 6 divided by 2 equals 3. 6 divided by 3 equals 2. Those 4 go together. And they take one, whichever one, and they have to write the other 3. as exercises over and over and over. Grade 3 should be around grade 3 as they start learning their multiplication tables and their connection between multiplication and division. You always have these four sentences that go together by just shuffling things around. So a certain combination might be a multiplication. Shuffling them around has a corresponding division. So now think of this sentence as this first one, where instead of a 2, I have 100. Instead of a 3, I have a question mark in a box. Instead of a 6, I have a 95. There's still a multiplication sentence that can be rewritten as a division sentence. And I want the division sentence that leaves the 3 on its own. It's this one. So I have my division sentence. If I just match this, 6 has the role of 95 divided by 2 has the role of 100 equals 3 has the role of question mark in a box. This is one of my division sentences, and because I'm trying to figure out the question mark in a box, I want that guy alone on one side. Now if the left side balances the right side, then the right side balances the left side, so it really doesn't matter which way you write it. I'm just going to turn it around because I like my symbol on the left. And then the only thing that is left is to realize that division is just an instruction for a fraction, the instruction version of the fraction. So I can go back to the start and say I've now figured out that 0.95 is 95 over 100. Now, of course, we knew that because we had an easy enough fraction to just understand decimal place values. So this was complete overkill. But when it comes to repeating decimals, this is the method. Because there, the decimal never ends, so I can't use powers of 10. It just doesn't work. So I need a fancier method, and this is going to be it. So I take an easy example, which I already know the answer, and see that this more elaborate, sophisticated method still works, and I can trust it moving forward. So it's very important to be able to defend what you do. Even though the student might not know what's coming up, you do, and there is a level of trust required. But at least I can defend it and say, look, Timmy, I know what's coming up, and we're going to need this. So while it's not too difficult a decimal number, let's focus on the method that we'll need moving forward. And let's use it on number 4. Now I have a repeating decimal number. Now I know all repeating decimal numbers have fraction representations. I just have to find it. This is going to be my method. And it's not something I made up. This is the method. I'm going to use whatever symbol I want. I'm going to use question mark in a box because it makes me feel comfortable. I'm going to let that represent the decimal number that I am working with. So I just have an equation then. If I translate this fully to a mathematical sentence, meaning an equation, I just have an equal sign there. So these two things are equivalent. Put them on either side of a scale, they're perfectly balanced. Behind this question mark in a box sticker is the fraction I'm trying to find. However, I can scratch this corner as much as I want to. It's not going to peel back, but it's there. Now it's a little different in terms of the decimal number I have here, in that the 4s never stop. They never stop. I'm simply going to move the move the decimal point to a position that steps around one of these repetitions. And because 4 is the only thing that repeats, I'm going to multiply by 10. So let's say here next, 10 times question mark in a box. I need to multiply 10 on both sides so that the balance scale is still level. If I multiply the right-hand side by 10 as well, I move the decimal place 1 to the side, to the right. And what I have is 4, and then still infinitely many 4s. They never end. I never run out of 4s on the right. The line simply means they are there forever. So if I move the decimal place once, there are still infinitely many 4s following it. But writing a bunch of them with dots, it's very precise and clean. So we use the little line. Okay? So the first thing I have to be happy with is that when I multiply a repeating decimal by 10 in this case, it moves one of those forward to the ones position essentially, and then still have infinitely many repeating. Everything is still in balance. I know that's a sticky point for some. All right. Now, the problem is, contrary to what I had previously, that was enough for me to not see a decimal number anymore because it was terminating. Here, unfortunately, my goal is the same. I don't want to see a decimal number. I don't know what to do with them. I know what to do with whole numbers, with integers. This one, still a decimal number. Huh. So if I think about the balance scale again, I have some stuff over here. I have some blocks or whatever. I have some blocks over here. If this is in balance, and I take, let's suppose all these blocks are identical. I take one of these blocks away, and I take one of these blocks away. Everything's still going to be balanced because I took the exact same amount on both sides. Everything's balanced. So that means if I subtract the same thing on either side, then the equal sign is still good. Everything is still in balance. The equal sign means balance. Now I'm going to just go to the right side first. What I want to take away is 0.4 repeating, because that is exactly the decimal tail here that I don't want. I can subtract anything I want. I want to subtract whatever the decimal portion is, which is 0.4 repeating. So that then, I'm just going to skip ahead a little bit, I'll have just a 4. I'm trying to get away from decimal numbers. I'm always, if you look at a common theme throughout what we're doing, we're always trying to relate things back to what is more familiar. When we look at fractions, we relate it back to an integer calculation because that's more familiar. When we look at a decimal conversion here, we're relating it back to integers because they're more familiar. However, I have to make sure that I do the same thing on either side. So I need to subtract by the same thing on the left as well. However, it's a little bit of an apples and oranges situation on the left. On the right, I was sort of speaking the same language. If there was a decimal number, I take away a decimal stuff. They understood what I wanted to do. Here, originally on the left, they have a bunch of question marks. Now I come in and want to take out a decimal number. They're going to tell me, no, I don't know what to do. you're right in that you need to subtract the same thing, but you're not speaking our language right now. We don't understand what you want us to do. Then I come back and say, well, my question mark in a box is exactly the same as point 4 repeating. These two things are equivalent. So instead of me saying, I'm just speaking the wrong language here. Instead of me saying take away a point 4 repeating, I can say take away a question mark in a box because they are the same. They're the same thing. It's like one is your formal name and one is your nickname that your friends gave you. If you go to your, well, maybe not your friends, uh, yeah, sometimes. If you go to your friends and someone addresses you in your uh, official name on your birth certificate, some of their friends might not know who that is because they only know you by your nickname. Maybe it happens. But if you refer, if your friend, if another friend refers to you by your nickname, oh, then that friend's gonna know who's being referred to. It's still you either way. It's just a matter of which name should be used for the group the group you're in, which side you're on. Still the same thing. And I have to subtract the same thing. So now on the left here, now they say, oh, you want to take away a question mark. Well, we have 10 of them. If you take away one of them, we'll have left 9 of them. I know you don't need the multiplication sign there, but that's nice. All right. So we have gotten to a point where we don't see any decimal numbers anymore. Phew, that's nice. Now again, multiplication sentence that if we use numbers, that's not strange to anyone. There are 4 of them. I'm looking for a division sentence that corresponds to this, but of course, I like my question mark alone on one side. It's going to be 4 divided by 9. You can't tell little Timmy, oh, divide on both sides of the equation. He's going to look at you like, what? I'm not doing algebra. I'm not in high school. I have no idea what you're talking about. But if you talk about multiplication sentences and equivalent division sentences, they've done this since grade 3. Put it in a language that he can relate to. And so, question mark in a box is 4/9. Go up here. Remember, your understanding might not be at the right level for little Timmy. You need to rephrase all these things. And we can easily. Easily. Yes, I'm working with equations. Yes, I'm working with a variable. Don't use those words. He doesn't know what that means. He's grade 3. Well, not grade 3 here. Grade 4, probably 5 these days. He hasn't done algebra yet. He hasn't even heard the word algebra. You can still do it. The concepts are the same. Logically, it's all the same. Sorry, I missed a YouTube comment here. Do you only put the line over the repeating numbers? Like 3 on the last question. Sorry, I'm very late to that comment. I don't know where you are. Whatever is repeating, yes, maybe this one you mean? The 8 never repeats again when you do the division. The 0 doesn't repeat either. You get into a loop and the 3's keep coming up. So only the repeating portion gets a line. Otherwise, it doesn't mean the same thing. If I were to say 1.083 with a line, that would mean 1.083083083, and that section repeats forever, and that's not the same anymore. No. Sorry, I'm not used to people commenting in YouTube. It's so rare, actually ever, anywhere. Everyone's super quiet. I've gotten used to just talking to myself, which is unfortunate, but true. So, See the similarities here? I handle them different. I do see them differently. I handle a terminating decimal in a much more convenient way because it's not as complicated. I don't need all this fanciness. I just don't need it. You can do it, but it's a too fancy a tool for the job. But when I have a repeating decimal number, well, that's a fancier job and it requires a fancier tool. And I want to do that in a way that is not just for me. If it was just for me and I have enough experience, I could probably guess and check my way through this. But for me to understand why this is 4 over 9, for me to potentially teach this, I need to have a logical argument that systematically gets me there with each step, not a big jump. That's how we do it. That's how you pass on knowledge. That's how you make someone else better. Honestly, that's how I make myself better because now I understand it better as well. Yes, if I've seen uh, this kind of decimal a lot, I start to recognize it's over 9. Zero point 0.6 repeating, 6 over 9. Sure, there are a lot of patterns here, but with enough experience, I can use that. Sure, but I pretend I have no experience. I need to figure out. I need to figure it out. How do I do that? You can't tell little Timmy, it's 4 over 9 because that's why I say it's what I say it is. Just accept it. No, no. That's how we get the vast population not having any idea about any math and scared to death of it because their teachers just forced patterns on them that they don't even see. That's not how it works. Just because people do it doesn't mean it's right. So now I see the 7 and the 2 repeating. That dot is it's not supposed to be there. So 2.72727272. First thing I want to do here is get rid of that whole number portion. I do not care about it. It's going to mess me up. Never ever use it in your argument because I don't need to. The 2 is not an issue. The repeating decimal is the issue. Get that 2 out of there. Sometimes it works perfectly and it won't mess me up. Sometimes it's just going to make this unnecessarily complicated. Never ever use it because I never ever need to. That's the first thing. So now I'm going to say, maybe I don't want question mark in a box. Maybe I want a little star to, whoops, I don't want to say it like that, to represent, bad habit, represent what I need it to represent. Then mathematically speaking, those two things are equal. Okay. I want to peel back this star sticker to see what is the fraction. And then once I see that fraction, I'll put it here and put it with the 2 and make a mixed number. I don't need that 2 in this argument. I only need to focus on the decimal portion. All right. So now I'm going to have to, I'm always doing the same thing in that I want to get the decimal point past the repeating section. And this time, 2 decimals are repeating. Oh, I just saw we're already out of time. I think we're going to have to pause here. I'll just do one more. So this time I'm going to multiply it by 100 because I need to move the decimal point twice so that I get 72, the repeating section, out. But of course, there are infinitely many 727272s repeating. So there's still infinitely many of them after the first 72. They never end. And on the other side here, of course, I have 100 of these stars. So unfortunately, this is where we have to pause. But if you want to, think about what would we do next? Matching it with the, where's the 4 over 9? There it is. Matching it with what we did here. Same argument. What would I do next? Can you finish it? And of course, I'll make a note. Remind me if I forget. We're at number 5. And we'll just take as long as we take. Because this is a step up in sophistication of an argument. It's not something we are necessarily comfortable with, which means we need to take our time. We need to slowly do one step at a time, because if I understand each step, going from this step to this step, this step to this step, this step to this step, okay, that makes sense. Okay, one more step. Then when I look back, I've done the whole thing. No single step should be an issue. When I string them together, I've actually done a whole bunch. But it takes time. It takes time. So think about this if you want to. It's okay if you don't. But unfortunately, we're out of time here. Are there any questions before we pause this discussion? All right. Until next time, then. Thank you.